Okay. If you have to miss, I mean, not if you skip. Okay, so if we look at this, everyone has the same correct answer across the board. And we're looking at the chemistry that's going on is that the nitrite is the pH active species. So when we look at lithium nitrite dissociates. Lithium's an alkali metal, so it has no pH activity. And nitrite is the conjugate base of the weak acid, nitrous acid. So we start off finding the Kb by Kw over Ka, and we get 1.4 times 10 to the negative 11th is Kb. Then we can plug that in. Kb is equal to the concentration of the nitrous acid times the hydroxide divided by the nitrite. We solve for X. X represents for us hydroxide, and we get 2.7 times 10 to the negative 6 molar. So from that we find the pOH, 5.58. Says nothing about temperature, so we assume pKw is 14. We're at 25 degrees. 14 minus 5.58, we get a pH of 8.42. And again, this seems like a reasonable answer because nitrite is the conjugate base, so it should be basic. It should have a pH higher than 7. So now let's look at what happens if we have a salt that contains 2 pH active species. If we have a salt that has a cation that is the conjugate acid of a weak base and an anion that's the conjugate base of a weak acid, then you have 2 equilibria. You will have your acid acting like an acid and you'll have your base acting like a base, and they compete. Now, for this class, because we're going to have competing equilibria, we will not calculate the pH. So no pH calculations in this class for this activity. There will be a lot of other pH calculations. We're not going to do that, but what we will do is predict, will it be acid or base? And the way we predict that is by looking at the Ka values and the Kb values. So if the acidic cation has a Ka that is bigger than the Kb for the basic anion, it will be acidic. If the basic anion has a Kb bigger than the Ka for the acidic cation, it will be basic. James?
For solving for the pH, do you just figure out what each individual is and add them, or take the difference between them? Is that it?
You don't. It's a lot more complicated. You write out the 2 equilibria, you add them together, you multiply the Ka times the Kb, and then you set up an ice chart and figure out what's going to really happen.
Okay.
And it just depends who is stronger. So for our purposes, we're just going to predict if it's acidic, basic, or if it's something we have to calculate. That's what we're going to practice when we start practicing what's in my beaker, which we're going to do hopefully a little bit later today in just a few minutes. Okay, so we look at the Ka and we look at the Kb and we just decide which is bigger. So let's look at this example. Will the pH of a 0.2 molar solution of ammonium cyanide be acidic, basic, or neutral? Well, ammonium, NH4+, is the conjugate acid of the weak base ammonia, and cyanide, Cn-, is the conjugate base of the weak acid, hydrocyanic acid, HCN. So we have to calculate the Ka for ammonium and the Kb for cyanide. So the Ka for ammonium is equal to Kw, 1 times 10 to the negative 14th, divided by Ka for Kb for ammonia, 1.8 times 10 to the negative 5th. So it is equal to 5.6 times 10 to the negative 10th is equal to the Ka. Now we'll do the same thing for the Kb for the cyanide ion. So Kb for cyanide is equal to 1 times 10 to the negative 14th divided by Ki, or Ka, not Ki, for HCN, 6.2 times 10 to the negative 10th. That's equal to 1.6 times 10 to the negative 5th is equal to Kb for cyanide. Now we look at these two numbers and we decide which is bigger. Which of those two numbers is bigger, the Ka or the Kb? The Kb is bigger, so it will win. So the solution will be basic. Can we tell exactly how basic just by looking? No. Now, we got a couple of I do math in my head wizards in this room. So for you I do math in my head wizards, do you see anything else here that could save you doing math at all? Right. So when you look at this, the Kb for cyanide is bigger than the Ka for ammonium. Now let's look at their conjugate Ks. The Ka for ammonium was bigger, and the Kb for ammonia was bigger than the Ka for the acid, so it's opposite, right? So if I look at the numbers here, I started off with my Kb of -5, and I got -10 here. Here I was -10, and I got -5. So you can calculate and say, well, this one's bigger, or you could say, well, this one is a smaller K, so its conjugate will be bigger, and you could save yourself the trouble of the math. Does that kind of make sense? So whichever way you do it, if you have to do the math or if you just think through it, on this next test, you may find, you're going to see the instructions are going to say, if you're doing something in your head, write down what you're thinking. Because you may look at something and say, oh, what's the pH? 7, and write it down. But writing down 7 on the paper isn't enough. I have to know why it's 7. And if you look at something and say, well, it's at the equivalence point of a titration of a strong acid, strong base, and it's pH of 7, then that's right, but I don't know that you didn't just randomly write down some number. So you may have to just make some little notes about why you know something if you're not calculating it. So be ready for that. Okay, go ahead and do this next one, and just do it at your seats, and then we're going to start practicing figuring out what's in my beaker. Don't look at the board. I'm just putting that on there so it'll be on the video and I can stop it.